Alright, so in this video I'm going to be explaining another important article about domain adaptation. The title of this paper is A Class-Aware Optimal Transport Approach with Higher Order Moment Matching for Unsupervised Domain Adaptation. So this paper in 2024. Unsupervised domain adaptation aims to transfer knowledge from a labeled source domain to an unlabeled target domain. In this paper, we introduce a novel approach called class-aware optimal transport, which measures the optimal transport distance between a distribution over the source class conditional distribution and a mixture of source and target data distribution. Our class-aware optimal transport leverages a cost function that determines the matching extent between a given data example and a source class conditional distribution. By optimizing this cost function, we find the optimal matching between target examples and source class conditional distributions, effectively addressing the data and label shifts that occur between the two domains. To handle the class-aware optimal transport efficiently, we propose an amortization solution that employs deep neural network to formulate the transportation probabilities and the cost function. Additionally, we propose minimizing class-aware high-order moment matching to align the corresponding class regions on the source and target domains. The class-aware higher-order moment matching component offers an economic computational approach for accurately evaluating the HMM distance between the two distributions. So these are three contributions. They propose a novel class-aware optimal transport that addresses the challenges of data and label shift, just like the previous videos that we talked about label shift. So we have in-domain shift, we have concept shift, we have label shift, and we have covariate shift. Again, I say that it's very hard to decouple them because they are very mixed. The second contribution is we introduce a class-aware high-order moment matching distance to accurately approximate the distributions of source and target domains in the latent space. And the third one is that they conduct extensive experiments to compare their proposed method, which is called cloth, with state-of-the-art baselines in standard UDA. So we consider this labeled data set of source domain, and this one is target domain. And given a class M, we further denote P sub M as the M's class conditional distribution of the source domain. The distribution with the density function. It means that their label is M, so it's M's class distribution. So in the given scenario with a total of n samples, comprising n sub s samples from the source domain and n sub t samples from the target domain, the source samples are denoted as x sub I and the target samples are denoted as this one. To capture the distribution of both domains, we define an empirical mixture distribution P. So this is a mixture distribution. It has source domain and it has target domain. So a mixture of them. We call it empirical mixture distribution. So you see the optimal transport distance between the two distributions. So this subscript M is the M's class. So when we go from EMS class, when you are in EMS class, the corresponding, the optimal transport is Ci sub m, because you have some source, but you have some targets. But this source, for example, because it's a multi-source, it could be multi-source. So we have the i's, because x sub I, as you see, all of them, we assume in this paper that it's a single domain. In contrast, as you see the title, it's not about multi-source domain adaptation or generalization. So it's just they care only about the class-aware optimal transport. So here, when we say x sub I, is just one of the samples. So we are not talking about multiple sources, but we are talking about multiple classes, because this is class M, this is class M, this is class 1. And for each of them, when you have a sample, because this could be a sample, but I mean, in my mind, I thought that, you can generalize this paper by saying that, okay, we can do that for multiple. So you can write an article and use this article as your baseline, saying that you can extend this idea, to the multi-source case. But here, the optimal transport distance between the two distributions, you see that P consists of atoms representing the source and target examples. And now we examine an optimal transport distance between the two discrete distributions. Our goal is to match both source and target examples to the source class conditional distributions, where a source example is explicitly guided to match the source class conditional distribution corresponding to its ground truth label. So we employ a feature extractor G to map both source and target examples to a latent space. And here we see the Wasserstein distance. And A is just the transportation matrix. And each entry, for example, AI sub M, as I said, that could be the probability of matching or transporting X sub I to this class M, or the optimal transport distance between P and PS. So we employ a feature extractor G to map both source and target examples to a latent space. Now, the optimal transport here in this equation can be written like this as well. To conduct domain adaptation, we aim to transport the target examples to appropriate class regions of the source domain. This can be achieved by solving the following optimization problem. So, given a data sample G of xi, and let AI be its probability mass, the ith row of transportation matrix. By setting the cost function as C equal to minus log of P sub M, minimizing this optimal transport distance encourages the following, these two. First, the source sample G of xi is G of xi sub S. It is matched according to Q, and then the target sample also should match. It is encouraged to move to a Q distribution with a high likelihood. And A sub I is inspired to be close to corresponding scaled one-hot vector. Minimizing the optimal transport distance through this optimization process encourages the clustering of both source and target samples under their respective source class distributions. In the subsequent sections, we will discuss how to solve the optimization problem, this optimization problem, and the definition of the cost function. So this is we call it amortization approach. The optimization problem can be solved analytically using Sinkhorn algorithm. However, this approach becomes computationally infeasible due to high time computational complexity, order of n squared for each iteration, which is quite high. So to this end, to address this computational challenge, one has explored a mini-batch version of Sinkhorn algorithm. Nevertheless, still it has bias. So in order to achieve accurate distribution matching solution, we propose an amortization solution for minimizing the optimal transport. So we employ a deep network called transportation network with M outputs, which allows to amortize transportation matrix. So given sub x sub I, we use the transportation network to predict the probability. And this probability distribution specifies the likelihood of matching or transporting g of x sub I to q. And this constraint is naturally satisfied. So the optimization problem can be easily solved with this approach. So for a source sample, g of x sub I is equal to g of x sub I sub s. And we can rewrite the optimization problem like this. And this is cross entropy loss. So we propose a loss function which has these two objectives. First, it should minimize the entropy of the prediction to encourage the transportation network to make clear decisions about where to move. Second, maximize the entropy of the averages of sum of tau of g for all target samples to encourage an equal movement to the class regions. So we minimize this entropy loss. H is entropy, H is here is entropy. So we explain how to define the cost function, drawing the inspiration from adversarial training. So the discriminator D is trained to distinguish, just like GAN, the discriminator is the distinguishes source from target and predict the labels for source. So this generator fools this discriminator D. The same GAN idea that we use here for domain shift problem. And the cost function Ln5 that we discussed captures the extent to which G matches, and we rely on the output of the discriminator. So the loss function can be expressed like this. So our objective is to move the source examples to entire region of target examples characterized by high values of D. So we propose minimizing the following problem. For target examples, our goal is to move the target examples to the entire region of the source sample examples characterized by low values of D. So we minimize this term. And we utilize a source classifier. This is source classifier that is trained on the source domain. And then this is loss of entropy, and we have discussed this as well. And this is your source classifier And they also talked about high order moment matching as well. So this generator wants to fool this discriminator, and we have transportation network and source classifier. This is the framework of this, the model cloth in this paper. So given a vector z, which represents a data sample in an adapted layer, we define a q-order moment of z is a q-dimensional tensor. So given two distributions, u and v, we consider this higher moment distance between these two distributions. And also they talk about class aware, but now this time about high order moment matching. And then they train it. So given their source and target, again, this paper is just single source, single target, but we care about multi-classes. And so the optimal transport is the optimal is this, the optimal of this. So we sample mini batch of source, then we update D. We sample mini batch of source and target, and then we update CT and generator. And we always use TSNE visualization algorithm because it's a visualization algorithm.